Welcome everybody to the lecture 9 of the inorganic chemistry course, and this lecture will really be serving as a bridge between what we've learned already and the sort of in-depth stuff we're going to be looking at in lecture 10. So we'll start by building upon what we've already learned about the coordination complexes, going a bit more in detail into the shapes they can form and the oxidation states, electronic configurations, things like that. Then it will serve as a stepping stone to our last lecture, which will be on crystal field theory, which is a lot more in-depth look at these complexes, why the colours that they are form, and a lot more of the electron interactions in these complexes as well. So we'll be looking at a couple of small topics and then how they will relate to the next video. So as I say, like a stepping stone. And in this first one, we'll be looking at oxidation states. So it's actually just a couple of slides, and I'll be doing it in the form of worked examples because I think that's a much easier way of describing how to calculate the oxidation state. Then I'll also be going to relate the oxidation state to the electronic configuration, which will come in very important in the next lecture, as I'll say on the way through. So first up, how to calculate the oxidation state. This is really the important thing and the bones of the lecture. So there are three components that we have in a metal complex that we can use to calculate the oxidation state of the metal. Well, first off, the oxidation state of the metal is one of these complexes, and I'll refer to this just as OSM. And then we've got the charge on the ligands, if this is present. I'll refer to that as ZL, and I'll use Z because we've used that in the Kapuscinski equation and stuff before to indicate charge. It's quite often used to represent charge. And then we've got the charge on the complex ion, so I'll call this ZC. And how this all relates together is that the charge on the complex ion is the sum of the charge on the ligands and the oxidation state of the metal. And if you remember that when we're looking at single atom ions, the oxidation state is equivalent to the charge. So essentially, the oxidation state of the metal is the same as, we could say, Zm, it's the charge of the metal. Like if you've got nickel 2+, the oxidation state of that ion has to be equal to the charge, so it will be nickel in the +2 oxidation state. So that's how all these three things combine. So we've got the charge on the whole complex is the sum of the charge on the ligands and the oxidation state of the metal. And usually, the thing we're looking for is the oxidation state of the metal. So we can rearrange this to give us the oxidation state of the metal equals the charge of the ligands minus the charge of the complex. No, sorry, that is actually completely the wrong way around. The oxidation state of the metal is the charge on the complex minus the total charges on the ligands. So I've got two examples here to show you how to do it. The first one is nickel hexaamine 2 ion, and the way you can know the charge on the ions, you'll actually get to know them as you go through and see them more regularly anyway. But if you're unsure of what the charge on the ions are, they're on that table that I gave last lecture on the naming one as well. So it has all the ligands, their names, what they're referred to officially in the naming structure, and the charges. You can also just pretend if what if it wasn't in a complex, and we know that NH3 is a neutral ion, a neutral compound. So in this case, it's a neutral ligand as well. So what this means is that the charge on the ligand, ZL, is in fact 0. So then if we put everything we want to know in this equation, we've got the oxidation state of the metal equals the charge on the complex, which is 2, minus the charge of the ligands. So we've got 6 times nothing, so we can just ignore this whole thing. And we see that the oxidation state of nickel is 2. So now if we go on to the next example, this one's slightly more interesting, tricky, shall we say? Not really, you're just dealing with ones. But if you check on that table, you'll see that the cyanide ligand is 1-, so it's a Cn- ligand. So now we actually have to deal with that term of the charge of the ligands. So in this case, the oxidation state of the metal equals the charge on the complex, which is -4, minus the charge of the ligands, and this is 6 times -1, because we've got 6 of these cyanide ligands and they've all got 1 negative charge. So then, yeah, this ends up being -4 minus -6, which is 2. So in this case, the oxidation state of iron is iron 2, or +2. Now on page 1268, there's a worked example box 28.2, and that's where I've taken these first two from. There's also a third question in there, so if you want to check for yourself how you do it, then go ahead and try that final question. So it's important to know what the oxidation state of the metal in the complex is for the crystal field theory we'll be coming to in the next lecture, because then we're going to be looking at the electronic structure of the metal, because this dictates a lot of things such as the colour and the shapes it actually creates. So we need to take that oxidation state and turn it into an electronic configuration. Now this is kind of revision from the first video, because we've actually seen how to do electronic configurations already, but I'll take these same two examples and show how to work through them. So the answers from last time, we saw that in the nickel hexaamine 2 ion that the oxidation state of nickel was +2. And as I was saying, when you've got a monoatomic ion, the oxidation state is the same as the charge. So we know that in this case that we're dealing with the nickel 2+ cation. So then to get from this, what we've worked out with the oxidation state, to the electronic configuration, we first need to write out the electronic configuration of the metallic element, which for nickel is 3d8 4s2. Now the second step is to move all the electrons into the d orbitals, because as I said in that first video, when a metal ion comes into a compound, the electron repulsions in the d orbitals are minimized, so it's actually more favorable for all the electrons to be in the 3d orbital rather than the 4s. So then we put all of them in the 3d orbitals, because there are actually space, only just, we're completely filling it then, to 3d10, and then remove as many electrons as we need to get to nickel 2+, which will then be 2, so we just have 3d8. So there are two steps we can go from just having a complex formula here, or complex ion formula, to working out the oxidation state and then taking that and working out the electronic configuration of the metal, which in the next video you'll see is key to everything in crystal field theory. So let's do it one more time with the iron example from the iron cyanide complex ion. So we said that the oxidation state of iron in this case was again +2, so the cation is iron 2+, and then we do exactly the same thing. So the electronic configuration of iron is 3d6 4s2. So we do the same two steps, put all the electrons into the d orbitals if there's space. In this case there is, it makes it 3d8, and then take off as many electrons as you need. So 2 in this case again, because it's 2+, so that leaves us with iron with an electronic configuration, or iron 2+, should I say, electronic configuration of 3d6. So as I said, it's a bit of revision from the first video, this section actually, but it does link it nicely to how you've calculated the oxidation state, and you'll see this is super important in the next lecture, as I've been saying.